So AIs are making predictions constantly, right? I mean, they're everywhere. But can you actually trust them? Like, really trust them? Well, there's this really cool technique that's designed to tackle that exact problem. I mean, think about it. You see it all the time. Your weather app, maybe a medical tool, it spits out a prediction and says, I'm 95% sure. But what does that even mean? Is that like a legal promise? Or is it just the AI kind of having a gut feeling? Okay, so here's the kicker. And it's a little unsettling. Most of the time, that number, it's not a guarantee at all. It's really just the model talking to itself, saying, hey, based on my own logic, this answer seems consistent. That is not the same thing as promising it'll be right 95% of the time, out here, in the real world. And that difference, well, it can be a really, really big deal.
So how do we fix this? How do we get away from this fuzzy confidence? Well, it turns out the answer is to totally rethink what we even mean by a prediction. And this new approach has a name. It's called conformal prediction.
And this is a huge shift in how we think about this stuff. Normally, an AI gives you one single answer, right? It says, the flower is this species. End of story. Conformal prediction, though, does something different. It gives you a set of possibilities. Think of it like a multiple-choice answer. Maybe there's only one option in the set, but sometimes there could be two or even three.
Now, this set of answers has a name. It's called a prediction region. And this is where the magic happens. Instead of some vague confidence score, you get an actual, rock-solid mathematical guarantee. The algorithm promises you that the real answer will be inside that set 95% of the time, or 99% of the time, whatever you decide. That's a real promise. And for anything important, that's a total game changer.
All right, I know what you're thinking. Mathematical guarantees sound super complicated. But the idea behind it is actually kind of simple. It really all comes down to asking one question. How weird does this look?
So let's walk through how it works. First, you start with all your data from the past. Simple enough. Then, you take your new unknown thing and you just guess. You make a hypothesis. You say, what if the answer is X? Now here's the clever part. You temporarily add your guess to the pile of old data, and then you score everything on a scale of normal to strange. If your new hypothesized point isn't one of the super strange ones, if it kind of fits in with the crowd, then hey, your hypothesis is plausible. The final prediction is just a list of all the guesses that seemed plausible.
Okay, that's still a little abstract. I get it. So let's make this real. We're going to use a super classic example from machine learning, figuring out the species of an iris flower. So here's the scene. We've got data on 24 flowers. We know things like their sepal length, and we know their species. Then a new flower shows up, number 25. We can see its sepal length is 6.8, but we have no idea what species it is. That's our mystery. And our mission, should we choose to accept it, is to figure out if it's a setosa or a versicolor. But we don't want just a guess. We want a prediction with one of those guarantees we've been talking about. All right, time to run the how strange test. Let's start with hypothesis number 1. Let's just pretend for a second that our mystery flower is a santosa.
Okay, so we pop that idea into our data and we crunch the numbers. And, it turns out if this new flower were a setosa, it would be a real oddball, a bit of an outlier. It would rank in the top 8% for strangeness compared to all the others. And by the way, that strangeness rank, that's basically what a p-value is in statistics.
Okay, cool. Hypothesis 1 is on the board. Now for hypothesis 2. What if this thing is actually a versicolor? We run the exact same test, and whoa, look at that. If it's a versicolor, it's not weird at all. It only ranks in the top 32% for strangeness. It fits right in with the rest of the data. See? This idea feels a lot more plausible. And you can see the difference clear as day. The setosa idea has a low p-value, which means it's a strange fit. The versicolor idea has a much higher p-value, meaning it's a much better fit. It's really that simple. A low p-value means weird, a high p-value means plausible. So now we just have to apply our rule. Remember the guarantee? We get to choose our confidence level. Let's say we want to be 92% sure. That means we're okay with being wrong 8% of the time. So our rule is dead simple. If any hypothesis is in the top 8% for strangeness, if its p-value is 0.08 or lower, we throw it out. And just like that, we have our answer. We look at the setosa hypothesis. Its p-value is 0.08. Uh-oh, that's right on our cutoff line, so we have to reject it. It's too strange. Then we look at the versicolor hypothesis. Its p-value is 0.23, which is way higher than 0.08, so we keep it. And that's it. Our final prediction region with 92% confidence has just one answer in it: versicolor.
And that little flower example, that really gets to the core of why this whole thing is so powerful. It's all about making a promise that you can actually truly trust. You know, the guys who invented this, Schaefer and Vogt, they put it perfectly. They said the most valuable part is the guarantee. If you decide you're okay with a 5% error rate, that's what they call epsilon, then the system promises that its set of answers will be right 95% of the time. Period. No wiggle room.
So let's just boil this all down. What are the big takeaways? 1. This is not another fuzzy confidence score. It's a hard mathematical guarantee on your error rate. 2. You can wrap this around pretty much any AI model you already have. 3. You get a set of possibilities, not just one wild guess. And maybe the most important part, you get to decide how much risk you're comfortable with.
I mean, this really changes how we should think about AI, doesn't it? It stops being this mysterious black box that's just, trying its best. Instead, it becomes a system that comes with a warranty, a built-in guarantee on its own predictions, and that changes everything.
So I'll leave you with this question. Just imagine a doctor using an AI to help with a diagnosis, or a self-driving car having to make a critical decision in a split second. What could we build? What problems could we finally solve if our AI came with a guarantee? If we knew for sure exactly how much we could trust it?